Welcome back. I'm excited because today we are starting something new, a daily series where we take one aeronautical engineering formula. So break it down completely and solve real examples with it. Just one formula a day in under 15 minutes, so you actually remember it. Today's formula belongs to the very first category on our master formula sheet, the standard atmosphere. And it answer a simple question. Why does it get colder the higher an aircraft flies? So this matters because everything else in aeronautics, lift, drag, engine thrust, even your airspeed indicator, depends on knowing the properties of the air the aircraft is flying through, and temperature is where that calculation begins. Here it is, the ISA temperature lapse equation. Um, so ISA temperature lapse equation T equals T0 minus L times H. So let's break down every symbol because in this series we never memorize blindly. T is the temperature we are trying to find at some altitude. So measured in Kelvin, T0 is a sea level temperature, and under the international standard atmosphere, so that's fixed at 288.15 Kelvin, which is 15 degree Celsius. That's our starting point, like sea level room temperature for the atmosphere. So L is the lapse rate, a fixed constant, 0.0065 kelvins per meter. So think of it as the cooling speed of the atmosphere as you climb, and H is simply how many meters above sea level you are. Now, here is the intuition, not just the algebra. Look at the formula. So we are subtracting uh, L times H from T0. As as H, the altitude goes up, that subtracted term gets bigger. So uh, T, the temperature must come down. So in plain numbers, so for every 1,000 meters you climb, the temperature drops by about 6.5 degrees. Okay, climb 5 kilometers and roughly 32 to 33 degrees colder than at the sea level. That's why the top of the mountain has a snow, while the base can be tropical. Okay, and why the airliner cruising at 10,000 meters is flying through air around minus 550 degrees Celsius. So one important limit to remember, this straight line formula only holds from sea level up to 11,000 meters. So that layer is called the troposphere. So above that in the stratosphere, temperature actually stops dropping and levels off. We will cover that boundary case separately. So okay, enough theory. Let's actually use this formula because a formula you can't apply in an exam or in the field is useless to you. Okay, we will do two examples. So one for a small aircraft cruising at 3,000 meters, and one for an airliner cruising at 10,000 meters. Okay, so example. So example one, a light aircraft is cruising at an altitude 3,000 meters. Okay, 3,000 meters. So find the outside air temperature. So step one, write the formula T equals T minus T0. T equals T0 minus LH. T0 minus LH. Okay. So T equals T0 minus LH. Step one, write the formula. Then step two, list our knowns. Okay. T0 is 288.15 Kelvin. L is 0.0065 Kelvin per meter and H is 3,000 meters. So step 3 substitute T equals 288.15 minus 0.0065 times 3,000. So step 4, calculate the second term first. Okay, 0.0065 times 3,000 equals 19.5. Okay, so step 5, subtract 288.15 minus 19.5 equals 268.65 Kelvin. Step 6, convert to Celsius if needed by subtracting 273.15. That gives us minus 4.5 degrees Celsius. So at 3,000 meters, it's already below freezing outside. It's below freezing outside, even on a warm day at the airport. So now example 2, temperature at 10,000 meter airliner. Okay, they're given and the steps are provided here. Let's see. So an airliner is cruising at 10,000 meters. Find the temperature and notice this is right near the edge of our 11,000 meter limit. Right. So same formula, same steps. T equals 288.15 minus 0.0065 times 10,000. So 0.0065 times 10,000 equals 65. Okay. 288.15 minus 65 equals 223.15 Kelvin. So in Celsius, that is 223.15 minus 273.15. So which equals minus 50 degrees Celsius. That is genuinely close to the real outside air temperature airline passenger fly through. So which is exactly why aircraft skin, fuel and hydraulic systems all have to be engineered for extreme cold. So three quick mistakes to avoid first. Don't forget L is per meter, not per kilometer. Okay, L is per meter, not per kilometer. Then if your altitude is given in kilometers, convert to meters before you substitute. Okay. So second, this formula is only valid up to 11,000 meters. So beyond that, the temperature is treated as constant and you need a different relation. So that's coming in a future session. Third, always check whether your answer is expected in Kelvin or Celsius. Add or subtract 273.15 to convert and double check your final number makes physical sense. Okay, so temperature should always be dropping as altitude increases in this layer. So temperature should always be dropping as altitude increases in this layer. Fine. Recap practice. So let's recap. T equals T0 minus LH. T0 minus LH. T0 is 280. T0 is 288.15 Kelvin. L is 0.0065 Kelvin per meter. Okay, don't forget. Valid from sea level to 11,000 meters, colder as you climb. So your practice question for today. So find the temperature at 5,500 meter altitude. Uh, so work it out using the exact same 6 steps we just used and drop your answer in the comments. So I will pin the correct one. Okay, so that's formula one down. Okay, so tomorrow we move to the next formula. So how pressure changes with the altitude, which actually builds directly on today's temperature equation. See you then.